All right, welcome back to the innovation stage brought to you by M12. Our next speaker is Mehak Mumtaz. She is the co-founder and chief operating officer at iLof. Please join me in welcoming her to our virtual stage.
Great. Well, hello, everyone. I am delighted to be able to present our work at this platform today. My name is Mehak, and I am the co-founder and CEO of Intelligent Lab on Fiber. We started iLof about 1.5 years ago with funding from EIT Health, Microsoft Ventures, and Mayfield. We're a company based in Oxford with an engineering center in Porto. And today I hope to be able to tell you about some of the really cutting edge work that we're doing at the intersection of physics, AI, and biology in order to create better tools to equip providers to offer optimal healthcare for patients. I'll be illustrating that through a tool we created in partnership with the hospital to tackle the COVID-19 pandemic. The current COVID-19 pandemic highlighted that globally, healthcare systems are not prepared with adequate tools to predict and manage infectious outbreaks. Within 1 year, 150 million people were infected, causing the death of over 3 million worldwide. About 20% of these patients, they develop severe or critical illness, meaning that after 1 or 2 weeks after the onset of symptoms, these patients might suffer respiratory collapse, shock, and multiple organ dysfunction. Absence of efficient treatment options and rapid disease progression continues to overwhelm healthcare systems across the world, particularly intensive care units that face shortage of trained professionals, equipment, and beds to attend all patients in need. It is now known that the risk for severe disease increases amongst the elderly, women, and people with underlying chronic health conditions, such as diabetes, cardiovascular, or respiratory disease. Yet, young healthy people may also become critically ill. However, there's no biomarker in use that can predict which patient might progress to severe disease at the time of diagnosis. Now, why is this important? Therapeutic management for COVID-19 is mainly supportive and primarily driven by the presence and severity of an individual's symptoms. A substantial proportion of patients initially presenting with mild symptoms are at increased risk of developing severe disease, and they would benefit from early and more aggressive intervention. Severe patients requiring specialized care and treatment were also the ones that overwhelmed intensive care units and led to difficulties in managing healthcare resources. There was hence a clear need to develop and validate risk stratification models that can provide early prediction of those individuals who are at risk of developing severe disease. This is what we set out to create using our platform technology in collaboration with a partner hospital. This tool was based on the iLof platform, which combines photonics with artificial intelligence to generate molecular signatures from patient samples that provide information about a patient's health or disease. We use a light-based tool that analyzes liquid samples, in this case, patient serum, by exposing them to a laser beam guided by an optical fiber capped with a polymeric microlens that focuses incident light on the sample. The optical harmonic potential propagated by the microlens, it causes the distortion of the Brownian movements of the particles present in the sample, generating a unique light scattering pattern. This backscattered optical signal is then collected by the same optical fiber, and it's transformed into a digital signal that's then processed and analyzed in the cloud. This processing includes phase matching, filtration, and normalization of the acquired raw optical signal of the sample, and then the signal is split into epochs of 10 seconds, and a set of 98 time and frequency-related features is calculated. Time-derived features, they provide information on the statistical aspects of the signal and describe its complexity and regularity, whereas frequency-related features capture the behavior of the signal in the different frequency bands. Together, these features gather information on the biophysical properties of small particles in serum, which can be called their unique optical fingerprint. Our AI algorithms then decode the complex signal resulting from the acquisition of a large number of scattered photons, converting them into relevant molecular signatures. This generation of meaningful molecular signatures from light scatter is only possible due to the use of advanced machine learning and deep learning models, and we use a variety of these approaches depending on the clinical questions we're answering. What's really unique about the technology is its ability to provide high-resolution molecular signatures characterizing blood samples in an unbiased and untargeted approach. This was particularly important for this work due to the lack of a specific biomarker of disease severity. However, our models can also include detection of targeted molecules within the sample, making iLof platform a very versatile tool. Finally, the tool is simple, does not require complex sample preparation or labeling, and it's also incredibly scalable due to the low cost of its component and its cloud infrastructure. These attributes make it the ideal frontline screening tool in any primary or secondary care facility. In this case, in order to develop the COVID-19 severity prediction models, we designed a prospective clinical study. Patients admitted at the hospital with positive COVID-19 diagnosis by real-time PCR molecular testing were enrolled in the study. Their peripheral blood was collected, processed into serum, and was analyzed using the iLof platform. Clinical information and demographics of the patients were also collected simultaneously. The primary outcome, which was the need for intensive care, was measured up to 4 weeks after diagnosis, and some of these patients developed severe disease that required ICU admission, and the remaining patients recovered with only mild to moderate symptoms and did not require intensive care. We then fed the optical fingerprints, patient age, sex, and comorbidities into a stacking ensemble model that was able to predict severe patients at the point of diagnosis with an AUC of 0.8. Through feature analysis, it can be seen that the top 20 features important for discrimination contained both optical features and comorbidities-related features, namely kidney, cardiovascular diseases, and immunosuppression. Importantly, we showed that this model outperformed other models that were created using clinical, laboratory, and demographic patient data. For example, a model that contained only age and comorbidities was able to identify severe patients accurately, but was only 25% specific. Furthermore, our model also outperformed an additional model created using age, comorbidities, and data from laboratory tests routinely measured for respiratory patients. These included CRP, IgG levels, and leukocyte counts. The main strength of the tool is in the simplicity of application in the clinical settings, whereby it has the advantage of using a single blood test with age and comorbidities that are easily collected through EHR data in order to make these predictions. Furthermore, we were also able to show that a single sample analysis can be used to answer distinct clinical questions. Using the holistic information provided by the patient optical fingerprint and feeding it into a separate machine learning model, we're also able to show that the tool can distinguish COVID-19 patients from patients presenting similar symptoms but distinct respiratory infections with an AUC of 0.88. To conclude, this work demonstrated that optical fingerprinting of patient serum samples collected at the moment of diagnosis, together with patient age and comorbidities information, can be integrated to provide an accurate severity risk assessment tool for COVID-19 disease. The low-cost, minimally invasive, and rapid pipeline required to collect the optical fingerprint of COVID-19 patients, it renders the use of this technology as a frontline screening platform to support clinical decision-making regarding patient surveillance and treatment timing. Furthermore, the holistic and agnostic analysis might be modeled to provide simultaneous information to assist COVID-19 patient diagnosis and prognosis. Hence, it provides a unique opportunity to develop a platform to not only manage current COVID-19 pandemic, as well as to rapidly respond to potential infectious disease outbreaks in the future. We're currently improving the performance and generalization of the models by increasing patient numbers, and we're testing the model in 3 independent cohorts with support from the European Commission. Additionally, we've also deployed the model and a prototype equipment in one of our partner hospital sites, and we're getting real-time feedback to improve our models. We'd love to hear from interested parties, researchers, clinicians, or hospital managers who might be interested in testing and using our tool. I hope that this whistle-stop tour provided you with a flavor of some of the work that we're doing at iLof and the potential of the iLof platform. Our ultimate vision is to use this low-cost and scalable platform to create rapid phenotyping and prediction tools through integrating large volumes of optical and patient data. We're currently also working in a few other areas apart from COVID-19. And if you'd like to hear more about either our COVID-19 work or any of these other applications, please reach out during the conference or later through our contact info below. I'd like to finish off by acknowledging our rockstar iLof team, our partners and colleagues at St. John Hospital and Oxford University for their support, as well as our investors, EIT Health, Microsoft Ventures, and Mayfield. We're also grateful to the European Commission for their support in scaling our tool. To all those attending today, I look forward to answering any questions and talking about how we might be able to partner to accelerate personalized medicine. Thank you very much for your time.
Wow, thank you so much. Thank you for sharing this with us. This has been an awesome presentation, and I know the audience is giving you a huge virtual round of applause. We really appreciate your time today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing AI exhibits. Thanks so much, and we'll see you around.